In this lecture, we shall study a single step potential barrier. Now, what is a potential barrier? If we have this kind of, potential energies, so for simplicity, we consider one-dimensional case. We plot the potential energy as a function of the position x. Then we can have this kind of situation. This is a potential barrier, and this is a single step potential barrier. You can have different types of potential barrier. Say you have 0 here potential energy, and then this, say V1, and then this is say V2, and you can here V3. So you can have different types of potential barriers, but for simplicity of presentation we shall consider for a single step potential barrier first. Remember, we are discussing one-dimensional problems in this chapter. So a single step potential barrier. We can have two cases here. Two cases. So case A, when the total energy of a particle is greater than the potential barrier height. And case B, if E is less than potential barrier height. This is our single step potential barrier. We have two regions here, region 1 and here region 2. And in the region, when x is from minus infinity to 0, it is the potential energy is 0, and when x is 0 to infinity, the potential energy is V naught. So we have this is known as single step potential barrier. First we discuss case A. What is our purpose of studying this? We shall find out how much wave will be reflected and how much will be transmitted. Say particle, quantum particle means de Broglie wave. So there will be a reflection and also there can be a transmission. We write down the Schrödinger equation. This is in 1D is this minus a square d square by 2m d square psi by dx square plus v psi equal to E psi, where E is the total energy. Okay, we have a particle on the left of this x equal to 0, and this particle is incident on this potential barrier, A part will be reflected and another part will be transmitted. In region 1, as we have identified two regions in the single step potential barrier. One is when x is less than 0 and region 2 is when x is greater than 0. If you write down the region here, write down the Schrodinger equation here. We denote the wave function in region 1 is psi 1, and in region 1 the potential energy is 0, so it's 0 into psi 1 equal to E psi 1. This equation can be simplified to this. Where alpha square equal to twice me by a square, where m is the mass of the particle. There are two solutions of this equation because this is a second order differential equation. One is e to the power I alpha x and the other is e to the power minus I alpha x. This one is the right going incident wave and this one is the left going reflected. This is incident and this is reflected. So the total solution or general solution in region 1 is psi 1 of x. Okay, then write down is a over I alpha x plus b to the power minus I alpha. A and b are the amplitudes of the incident and the reflected wave respectively. This one is the right going. We say this is psi incident and this is psi reflected. Now in region 2, we write down the Schrodinger equation and this is denote the wave function by psi 2 in region 2 and here the potential energy is V naught. You see this is V naught. This equation can be rewritten as this, and beta square here is twice m by square and E minus V naught. The solution also, we have here two solutions and we shall take only the right going one, because there is no barrier on the right of x equal to 0, so there is no question of reflection. So we have only transmission. Let us say this is C I beta x. This is psi transmission. No reflected wave in region 2. Okay, now what we are going to do, we are going to find relations between the reflected amplitude and this C is the transmitted amplitude and the incident amplitude A. And ultimately we shall define a quantity known as flux, and we shall find reflected flux and transmitted flux in terms of incident flux. A quantum particle is equivalent to a de Broglie wave. We know this, and that is why we are discussing this, the waves, de Broglie waves. Okay, now we have psi1 is a to the power I alpha x plus b to the power minus I alpha x, and psi2 is c e to the power I beta x. We have also relations alpha square equal to twice m e by h cut square, and beta square equal to twice m by h cut square e minus b naught. Okay, now we shall apply the boundary condition. We shall apply these boundary conditions because we are now going to find relations between B, C, and A. We have two boundary conditions. One, we have one boundary at x equal to 0, so we'll have to take psi1 is equal to psi2 at x equal to 0. Another boundary condition we will have to apply is the first derivative of psi1 with respect to position must be equal to the first derivative of psi2 with respect to position at x equal to 0. Okay, so we will apply these boundary conditions and we'll see the relations between A, B, and C. So if we apply boundary condition 1, we'll have A plus B equal to C, because at x equal to 0, this e to the power 0 means 1, e to the power 0, 1, e to the power 0, 1. So psi1 equal to psi2 will give us A plus B equal to C. So boundary condition 1 gives us A plus B equal to C. Similarly, boundary conditions 2 will give us what is the boundary condition 2 is first you have to take derivatives of psi1 and psi2, and then you put x equal to 0. So we'll have, if you take derivative I alpha A and here minus I alpha B will be equal to I beta C, because x equal to 0, A to the power 0 means 1. So we'll have here I alpha A minus I alpha B equal to I beta C. So if you now substitute C from this to here, we'll have alpha A minus alpha B is equal to beta and C equal to A plus B. So we'll have alpha minus beta into A equal to alpha plus beta into B. From this we see that B, the reflected amplitude or the amplitude of the reflected wave is alpha minus beta divided by alpha plus beta into A. Similarly, if we substitute B from this equation to here, we will get alpha A minus alpha B and B equal to C minus A equal to beta C. So it will be twice alpha A and here alpha plus beta into C. So C is twice alpha divided by alpha plus beta into A. Okay, now we have found out the reflected and transmitted amplitudes in terms of the incident amplitude. Okay, and we would like to find the flux, incident reflected flux and transmitted flux in terms of incident flux, and the flux is defined by this. Velocity into probability density, which is wave function modulus square. Now we have incident wave is this one, and reflected wave is b to the power minus I alpha x, and transmitted wave is wave function is and we need velocities. We know that alpha square equal to twice m e by square, and in region, this one was in region 1. In region 1 there is no potential energy, entirely is kinetic energy, so we can write down this E is half m p incident square. So this one will be m square v incident square by scattered square. From this we can find out v incident equal to alpha squared by m, and which is the reflected velocity, because it is in region 1. Similarly, we can find velocity in region 2 is beta square is twice m by a square, and this is E minus B naught. And you see the total energy minus potential energy, so this is also kinetic energy, so twice m by a square, and this is half mv transmitted square. This is m square v transmitted square divided by a square. From this relation we can say that V transmission equal to beta A square divided by M. Okay, so now we have found out this incident velocity, reflected velocity, and transmitted velocity, and we can calculate the flux, from this relation, and we shall see how these three fluxes are related. Okay, so incident flux, so is V incident into modulus square of the incident wave, and this is alpha is cut by M, and this is A to the power I alpha x modulus square. This one will be alpha is cut by M and modulus of A square. And the reflected flux, so is V reflected and then modulus square of the reflected wave function, and V reflected is also alpha is cut by M, and this one is B to the power minus I alpha x square. So this is alpha is cut by M modulus of B square. And transmitted flux, this, and this one was beta is cut by M, and this is C to the power I beta x modulus square. Okay, this is transmitted flux. This is reflected flux. And this is incident flux. Okay, now if we add the reflected flux and transmitted flux, what we see? And now substitute the values of B and C in terms of A we have found out earlier. And this B was alpha minus beta divided by alpha plus beta. This. Okay, if you take common, alpha is cut by M, then we'll have here this. This will be beta by alpha common modulus of A square. So if you simplify this, then we get this, and we know if we take common 1 by alpha plus beta whole square, then you'll have alpha minus beta whole square plus 4 alpha beta. This one is nothing but alpha squared by m, and this is alpha plus beta whole square, and here alpha plus beta whole square. Now this is alpha a squared by m modulus of a square, but which is nothing but the incident flux. So what we get sum of the reflected flux, and the transmitted flux is equal to the incident flux. This is like a conservation equation. Therefore, the reflected flux and incident flux, transmitted flux is equal to incident. If we divide both sides by F incident, then we get and we call it R, and this is T equal to 1, where R is F reflected by F incident and T is F transmitted by F incident. This R and T are called reflection coefficient, and T is the transmission coefficient. T is transmission coefficient. Okay, next we shall consider case B. This is will be very short. Now here is total energy is less than the potential barrier height. This is region 1 and this is region 2. Now in this case we do not consider region 1 because we will be interested only in the in region 2. So in region 2 the Schrodinger equation becomes this is the wave function psi2 is in region 2, and here v naught psi2 equal to e psi2. Now this equation can be written as d square psi2 by dx square minus gamma square psi2 equal to 0, where gamma square equal to twice m by a square. Now it is v naught minus e because v naught is greater than e. So make this quantity positive. We have here put minus sign. Now this solution, there will be two solutions. One is e to the power gamma x and another is e to the power minus gamma x. These are exponential waves. But you see the first solution, this one will be discarded because this one will not satisfy postulate 1 of quantum theory. Since gamma is positive, we take it real because v naught is greater than e, so gamma is positive, and when x tends to infinity, then this solution becomes infinite. This is not acceptable. Here no problem because we have x range is 0 to plus infinity because we are considering region 2. So the appropriate solution is the second one, and so we write down psi2 of x is equal to g e to the power minus gamma x. So it is an exponentially decaying wave. The probability density in region 2 of finding the particle is, we denote it by rho 2 of x, and this is modulus of psi2 square, so which is modulus of g square and to the power minus 2 gamma x. Now we want to plot this probability density with respect to the position. Now if we plot this probability density as a function of position, and let us suppose that when x equal to 0, so is x equal to 0 means 1, so is this is modulus of g square. Now you see it's exponentially decaying. This is twice gamma x, so we'll have like this. If we change the gamma, then we can have another like this. Okay, like this. So along this direction, increasing gamma, to taking different values of gamma, and increasing gamma means along this direction, means as you increase gamma means you increase v naught, because gamma is related to this v naught. This E is total energy constant, M is mass constant, E squared is constant. So as you increase v naught, gamma increases, and as gamma increases, this probability density decreases because we have e to the power negative minus 2 gamma x. And this is usual that the probability density will decrease as you increase the external, the potential barrier height. That means we increase gamma. Okay, this is the end of today's lecture, and in the next lecture we shall consider general potential barrier problem.